Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the content of the universe, how things evolve, how things interact, a lot of the cool stuff happening inside the universe. I love being a physicist, I love studying cosmology and cool stuff happening inside the universe, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, this is an interactive stream. The idea here is that you people can ask me anything you want about cosmology, about physics, about academia, about myself. This is an Ask Me Anything. This also means that you decide which direction this stream goes. Depending on the questions you ask, we will take this in a different direction. So you have almost complete control over where we go. Of course, I will always try to guide it towards my favorite topics. I see some of the regulars coming in already. Hey, Scott. Hey, Ben. Hey, David. One of the 3 or 4 Davids who follow here. Great to have you all in here, as always. So if you haven't... Messing up my intro again, I've been doing this so long, you'd think by now I would know my intro by memory, and yet every week I'm so like, wait, how do I start these things? What am I supposed to say? Who am I? Standard thing to happen. Anyway, welcome to any first-time viewers. Welcome back to any regulars. It is great to have you all here, as always. Paul, glad to hear you are not driving this time. Welcome. We're in a cafe. I believe you've been in random places last time. It's great to see you as well. Mito, great to see you as well. Welcome, everybody. If you haven't done so yet, please do subscribe to the channel, leave a comment, like the video, do all of the usual YouTube things. It really does boost engagement. And then I get a lot more people in here. All of the stuff that you do to boost engagement gets more people in here. And then I get to talk to more people about all of the cool things happening inside the universe. Cool. So yeah, I'm a theoretical physicist. I study stuff that happens in the universe. That's a very broad topic. Specifically, I study stuff that happens in the very, very, very early universe. Up until now, or until recently, I've always worked on dark matter, cosmic microwave background radiation. Now I work on gravitational waves. These are all buzzwords you are all always welcome to ask me about. So as always in these streams, this is a purely interactive stream, so you can ask me whatever you want. This is an Ask Me Anything. I do not have a topic prepared today. So we will talk about whatever people in the comments want to ask about. I see we have another David in here, and Ange, great to see everybody joining. As always, great to see all of the regulars, great to see some first-time viewers. No matter how many times you have or haven't been here, it is great to have you in the comments. You are always welcome back here. Now, I was thinking the other day, it seems like I've been doing this for almost 8.5 years now, and there are some of you who've been here since the beginning, and it still amazes me that you come back every week, and yet here you are, still coming back, asking questions, and that is very, very cool. Love to see you all here. Okay, so as always, you can ask me questions about anything you want. I see we already have a question in here from Scott. They seem to have figured out the moon's origin with Theia. Any idea what happened to whatever collided with Venus and Uranus? No. So there's a lot of ideas about where the moon could come from, our moon and other moons in general, because from what we've been able to see, a lot of people here do have a lot of planets seem to have moons. And there's a lot of different ideas as to where the moons could come from. Some of them are, for an example, in our case, it seems like the moon is actually a chunk of Earth. Something hit us at some point, hit the Earth, like a big asteroid came and hit the Earth and kind of ripped a chunk away, and that chunk is the moon. In other planets, you have different ways of creating moons. For an example, you can have planets that are just form as two objects and are not big enough to pull each other together, which is the case of Pluto. Jupiter has like 64 moons, I believe, 65. They keep finding new moons of Jupiter. Some of those will be just, in general, space debris or space rocks that have just gravitated towards Jupiter. Some will be from other objects smashing together. But it does seem like our moon came from an asteroid, which is nicknamed Theia, crashing into us and kind of ripping a part of the Earth away very, very, very early on. So that is, in general, the origin of our moon. As for other planets, not completely sure. Other planets' moons, I don't know off the top of my head where they all came from, but there are plenty of moons out there and plenty of different formation styles. This is not a new hairstyle. This is simply my hair has decided to be unruly again today. So it is doing whatever it wants, but nah, it's Sunday. I don't bother styling my hair. Not that I style my hair any day of the week, to be honest. I can't be like, it's Sunday, my hair's messy. My hair's just messy because life is too short to mess with my hair. Hair does whatever it wants. And as always, this is not a cosmetology stream. This is a cosmology stream. As Paul is saying here, until physics and cosmology is 100% figured out, you should all keep coming back. That is absolutely very true. So you should all keep coming back because we're not going to figure out all of physics and cosmology anytime soon. So please do keep coming back. There's always going to be new things to talk about, new questions, new discoveries, new things happening. And there's always some of my favorites we can revisit if not. So yes, that's why you keep coming back every week, because I haven't yet told you what dark matter is. Until we figure out what dark matter is and every other question in cosmology, you should all come here every time. So you didn't get the YouTube notifications? Sorry to hear that. I know sometimes it can be a bit buggy, but in general, I'm on every Sunday at the same time. You can also follow me on Twitch. This should be going out to Twitch as well as to YouTube. And on Twitch, there is a scheduler where it shows when the next stream is. And if I'm cancelling it, then you will just see that on Twitch, it disappears. So a good way to check is if you see a stream announced on Twitch, then it's going to happen. And on YouTube, I always set up the streams at the latest, like 6 or 7 hours in advance. So you can always find the video in advance or the link to the video in advance, even if you don't get the notification. And in general, you can expect me online Sundays 8 p.m. unless something in my life gets in the way. Everyone changed their screen names to David on April 1st. Yeah, that would be very funny, but I guess you should coordinate that privately, right? If you tell me you're going to do that, it's going to be less fun. But is the 1st of April even a Sunday? I don't believe the 1st of April is a Sunday this year. And isn't 1st of April over Easter, in which case there won't be a stream? But yes, feel free to prank me like that. If you all want to change your username to be exactly the same name, I would personally find it very amusing. Just heard about submoons yesterday. I wonder how many levels of nesting are possible. Well, any object that is gravitational, any object in the universe can have other objects orbiting around it, right? It's just a question of size. You can calculate what is known as the Roche limit for any object. The Roche limit is kind of the place where it's stable to have moons, or how close a moon would have to be in order to actually crash into the planet or be absorbed by the planet. So then you can have a moon orbiting around a planet. But if that moon is big enough, you could have a submoon orbiting around that moon. And how many nesting levels are possible? Basically, as far down as you want to go, because as long as you have something that is somewhat spherical orbiting, you can have a moon around it. So you can have submoons, so moons can have their own moons. Within the solar system, we have not observed anything substantially submoon-like. So as far as we know, our moons do not have submoons, but it is entirely possible that we could have submoons. There's no reason why we wouldn't have submoons. So that is a possibility. Yes, those of you in the US get a very nice solar eclipse on April 8th. I can't remember if it's a total one or a partial one. I think there is going to be some region of totality across the US. For those of you not in the US or North America in general, you will probably not see the eclipse. So there is another eclipse happening on April 8th, and it is mainly visible from North America and United States, Canada, kind of around there. The rest of the world might not get much of it. And I feel like there's now 3 or 4 eclipses in a row that haven't been visible but from Europe, and it's kind of annoying. Come on, guys. It's like when in all sci-fi films, they always invade America first, or there's always America first. Sci-fi films like doing this, especially Hollywood. And now they're bloody doing it with eclipses, and the US is getting all the eclipses, and Europe is missing out on the eclipse. Anyway, if you miss the eclipse in person, for whatever reason, be it that you're in a different country or that it's cloudy, there are always live streams of the eclipses set up, and it is always very fun to just tune into official live streams and watch the eclipse on your computer. It's not the same, but it's still fun to do that because eclipses are very fun to watch anyway. Oh, there will be totality in Cleveland. Excellent. So yes, if you get to see that, please do. If you're in a place where you can see the eclipse, please go and watch it, obviously in a safe manner. Please don't stare directly at the sun. It is not good for your eyes, but it is very good to witness an eclipse. I have seen a few in my life, and it is always very fun. But please, if you're looking at the eclipse, do it in a safe way. Remember to protect your eyes. Do not just stare at the sun. It is very much not worth it. But eclipses are worth seeing if you take the right precautions. Okay, comment here about galaxies. I have heard there are 100 million black holes, not galaxies. Okay, question from Ben. I have heard there are 100 million black holes in our galaxy. How many primordial black holes do you predict there are? I love this question. So let's just recap what we mean by primordial black hole, what we're talking about black holes here. I see there's a lot of a lot of comments here. I will get to those in a minute. Let me just go to this one. As always, I will try to get to all the questions. There might be some delay because I'll spend 10 minutes answering one question and then the questions pile up. But usually by the end of the streams, I do get through all the questions. So please be patient. If I don't answer your question, please feel free to ask again. But let's go through, as always, in the order in which they appear, unless it's convenient for me to change the order. So you've heard that there are 100 million black holes. How many of these are primordial? So a black hole is basically a region of space-time that is so dense that nothing can escape, not even light. In order to escape the gravitational pull of a black hole, you'd need to travel faster than light in a vacuum. As far as we know, nothing in the universe can travel faster than light in a vacuum. This means that nothing can escape the gravitational pull of a black hole. Okay, we know black holes exist. There are several different types of black holes we can think of. There are the standard black holes that we would think of, which are kind of stellar. We call them stellar mass. YouTube didn't ping you, Prash. You're not the only one. Apparently, YouTube notifications are a bit buggy today, so sorry if you didn't get the notification. You can watch the replay to see what you've missed in the first 12 minutes, but not much. Okay, so most of the black holes that we think of are stellar mass black holes. This means that their mass is about the size of a couple of stars, or 30 stars, 10 stars, 50 stars, kind of about a few stars put together. And these black holes happen when a star reaches the end of its lifetime. A star is a constant battle between gravity pulling things inwards and pressure pushing things outwards. As the star is burning its hydrogen into helium, this is going to push outwards. But the gravitational pull of these objects is going to pull things inward. So it's this constant battle. As a star reaches the end of its lifetime, it's going to go through a phase where it's going to grow quickly. And then gravity is going to win and take over. Hey, Abyss, great to see you as always. So then gravity is going to win and take over, and the star is going to collapse. Once the star collapses, so you get it going outwards, it's going to explode as a supernova probably, and then collapse as a black hole. So you can form stellar mass black holes by stars reaching the end of their lifetime, exploding a supernova, and then collapsing. Depending on how big the star was before it collapsed, you will either end up with something known as a white dwarf, which is kind of like a dying star, a neutron star, which is a super dense star but not dense enough to be a black hole, or a black hole. These are the ones where we think there's like millions of these black holes in every galaxy, the stellar mass ones. Another type of black hole you can have is what we call the supermassive black holes. Supermassive black holes are black holes that are billions or millions or billions of times the mass of the sun, or the mass of an average star. And these are enormous. If you think you take millions of suns and you condense them into a black hole, that is a huge thing. And we think there is a supermassive black hole at the center of every galaxy. So supermassive black holes, massive, huge black hole, center of every galaxy. There's a fun chicken and egg question of what came first, the supermassive black hole and then the galaxy forming around it, or the galaxy forming and then the black hole like being at the center of the galaxy because of all the gravitational attraction. We're not completely sure how supermassive black holes form because it's so massive. Some ideas are that you could have a lot of black holes smashing together. Eventually you end up with a supermassive black hole. Once some stars at the center of the galaxy start falling in as well, you can end up with really big black holes. And the third type of black hole we can think about is what is known as a primordial black hole. Primordial black holes are a hypothetical type of black hole that would be formed in the very early universe. So in the early universe, you had regions that were very dense and regions that were less dense. When we're talking about primordial black holes, what we're saying is there could have been regions of the early universe that were so dense that they directly collapsed to form a black hole without going through the whole stellar evolution phase, without needing a star. So primordial black holes would have formed in the very first few seconds after the end of inflation, or even at the end of inflation, depending on how you want to form these. These primordial black holes could have been growing ever since then, and they could explain a specific region, like something of a few solar masses that we haven't been able to completely explain, you could explain with primordial black holes. So these three types. There's also the idea that if you start with primordial black holes, a lot of these could smash together, and this could eventually lead to the supermassive black holes. So we have these three types. We know for sure that there are supermassive black holes at the center of galaxies. We even have been able to see the supermassive black hole at our own galaxy. See in quotation marks, because of course a black hole by definition does not emit light. So when you photograph a black hole or when you look at a black hole, what you actually look at is everything falling into the black hole. So you see everything moving around a big gravitational object that you can't see, and that is the black hole. So we've been able to find supermassive black holes, we've been able to find normal black holes. Primordial black holes are still hypothetical. We do not know if primordial black holes could actually have formed in the early universe, if at any point there were the right conditions to form these primordial black holes. So the question was, there are millions of black holes in our galaxy. How many of these are going to be primordial? How many of these are going to be stellar or normal black holes? The answer is it very much depends on what you think about primordial black holes. Because depending on how primordial black holes are formed, depending on how primordial black holes, if they're all formed instantaneously or if it's a gradual process, if they're all formed at the same mass or not, this would change the answer. So it's very difficult to answer the question of how many black holes in our galaxy could be primordial black holes, because we don't know how many primordial black holes might have been produced. So it very much depends on who you ask. Some people think that all black holes could be primordial black holes. Some people think that all black holes that in our galaxy are going to be stellar black holes. And there's always kind of the more favorable argument that we know that stars exist. We know a lot of stars end up dying and leaving, all stars die. A lot of stars end up dying and leaving behind a black hole. So it's a lot more logical to think of the black holes in our galaxy as being stellar mass or stellar black holes, because we know that this is a sort of process that definitely happens. Whereas the whole primordial black hole thing has so much uncertainty that it's very hard to say if that's actually a thing or not. So it's a very cool question. I love the question. I know that was a very long answer, but yes. So what fraction of these black holes could be primordial? I don't know, and I wouldn't want to give an exact number because there's so many things this could depend on. So it's not something we can clearly say of this fraction is primordial black holes. But because we have found stellar mass black holes or stellar black holes, those are the ones we tend to think about. Okay, let's see. There was comments here about the eclipse. Eclipse was great experience in Hungary, yeah, in 1999. I think if you get the opportunity to witness an eclipse, definitely do it. As I said, safely, please. But watching an eclipse is a very cool experience, and if you get the chance to do it, you absolutely should. H.G. Wells' Martians invaded Britain first and destroyed lots of places. Yeah, see, this is the thing. Sci-fi authors always kind of put it with either their own country first, or if you're a Hollywood movie, the US first. Unless they want to do warning shots, like in the film Armageddon, where all of the small asteroids destroy Europe first. There's one in Paris, there's one in London. The US is mostly untouched, but of course the biggest one is heading for the US, of course. But then, Bruce Willis saves the day in the movie that it has the most scientific inaccuracies of any film. I think someone counted at some point there were over 100 scientific inaccuracies or scientific mistakes in Armageddon, but that's not a film you watch for scientific accuracy, is it? A lot of these disaster films, you don't watch them for scientific accuracy. Okay, let me just go through the comments because I saw there was one about moon landings that I do want to spend some time on, so I'm going to come back to that in a minute. Let me just go through all the comments very quickly, and then we'll get back to that just to make sure what we're doing here. So there's a comment on the topic of black holes. There's a comment here from Abyss. Conversation about Kerr's new paper suggesting that black holes might not have a singularity. That is an excellent question. That is one I'm not going to discuss today because that is one that I would need to actually finish reading the paper first. And to be honest, every time I've read that paper, I have stopped halfway through. So just to give everybody a bit of context, one of the people who's most important in black hole research and did some pioneering research put out a paper recently saying something we all assume about black holes might actually be wrong. This is very interesting, but I have not had time to fully come up with my own opinion on this or digest this in a way that I could then explain it to you all. So this is something that is pinned in my mind for a future stream where I will do a whole stream about that once I figured that out. So Abyss, I will not talk about that today, but that is an excellent question. And that is one we can definitely come back to at some point. Sticking on the topic of black holes, before we move on to the other very good questions I see here, there's a question from Prath. Is it possible that intermediate mass black holes don't exist because there's a very short time frame between stellar mass black holes coalescing and forming supermassive black holes? Yeah, so this is what I kind of alluded to just now, but didn't go in depth about. There is something known as the mass gap. So we know how small black holes form in terms of stars, And then there's some bigger black holes, but there's this region in between, this kind of intermediate thing. Like, why don't we see black holes that are 1,000 times the mass of the sun? Why don't we see black holes that are a million, or like 2,000, 10,000 times the mass of the sun? Why is it either stellar size or supermassive? This is something that we don't have a clear answer to. There's quite a few explanations there, but it could be that there's a small time, as Preth is saying here, that once you've got a black hole, it will very quickly find other black holes to form together. Now, this might seem weird, but one way to think about it is you often have star-forming regions, right? A nebula, those very pretty pictures that you have, like the pillars of creation and all those things, those are nebulas. And that is just a star factory. That is a region where you are producing a lot of stars. It's kind of easy to think that in a nebula, you might produce stars of a similar type, which means these stars might have a similar lifetime. So when some of these stars end up as black holes, it's not just going to be one or two, but there might be a cluster of black holes suddenly, and then these are going to be gravitationally attracted. So it is possible to think that there's a short time frame for stellar mass black holes before they become supermassive black holes. On the other hand, we do think there's millions of black holes, stellar mass black holes in our galaxy. So then there's a question of why haven't all of those become the biggest ones? Is it either black holes are completely isolated and stay kind of stellar mass, or they're clustered together and you get a supermassive black hole? Is that the answer to the mass gap? We're not completely sure, but it is a very interesting hypothesis. So I love all the black hole questions. Black holes are such a fun topic, and there's just so much to do with black holes. Okay, let's go back to the question. There were some very cool questions here, but there is one. Oh, there was another black hole one. Okay, another black hole one from David Howden. Now I'm doing the bad thing if I'm jumping about in the questions, which means at some point I'm just going to have to go through from the start and make sure I've answered all of them. But for now, we're jumping about through the questions. There's a question by David Howden here of, if inflation happened again, would it rip a black hole apart? Would it allow stuff to escape it? Inflation can exceed light speed, if I recall previous broadcasts. Excellent question. So inflation is this hypothetical period of exponential expansion in the early universe. So if we look at our standard maps or our standard diagrams of the history of the universe, we always start with this tiny, tiny pinprick, and then we have inflation, and then everything else happens. So inflation is this hypothetical period where the universe grew exponentially. Now, cool things about inflation deletes the memory of anything that came before it, which means we have no idea how long inflation lasted, what triggered inflation, what happened during inflation. It's just the idea that at some point, in order to match what we see in the universe today, we think in its infancy, the universe had to grow exponentially for some amount of time. Now, inflation itself, I've said many times, you've all heard me say this, nothing in the universe can travel faster than light in a vacuum. However, space-time itself is not in the universe. Space-time itself is not something that is in the universe, it's something that we use to describe the universe itself. So space-time can expand faster than light in a vacuum. Indeed, during inflation, during this exponential growth, the universe would have expanded faster than the speed of light, and there is no such restriction on the space-time itself. So you can have space-time expanding faster than the speed of light. This does not contradict things. This very much goes in hand with our other theories of how the universe works, because when we're talking about the expansion of space-time, we're not talking about something moving through space-time. There you have the limit of the speed of light. What we're talking about is the fabric of the universe stretching. And for this, there are no upper limits. So during inflation, you can indeed have regions of space-time traveling faster than light in a vacuum. Could inflation rip apart a black hole? Now that is very interesting. Let's just imagine that for whatever reason, we trigger another period of inflation. What would happen? Would it rip apart black holes? Would it rip apart stars? Would it rip apart everything that we know? And to answer that, we can look at another parallel, another thing that we know that is happening. So we know that the universe is currently expanding again. So the universe, after it went through this initial inflation period, was expanding, but a lot of people thought this expansion was going to slow down and eventually go the other way. However, what has happened is that this expansion has increased. The universe is expanding faster today than it was in the past. And the reason we have for this is dark energy. So the universe as we know it has three main components: everything you see, everything you're used to, everything from me to my tea mug, which is a good reminder that I have tea, to the stars you see at the night sky. All of this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There is another 26.2%, which is in the form of dark matter. Dark matter is this weird type of matter that doesn't interact via the electromagnetic force, but it does interact gravitationally. This means that essentially dark matter is invisible, but we know it's there based on the gravitational effect it has on other things. Then there is this remaining 69%, which is in the form of dark energy. Dark energy is what is driving the accelerated expansion of the universe. Dark energy accounts for 70%. It is this negative energy that's pushing everything outwards, and that's pretty much everything we know about dark energy. But we can use dark energy as a proxy to think about inflation. So currently the universe has this ongoing battle where on small scales, things are gravitationally held together. We're still in orbit around the sun. We still have our moon in orbit around us. We are moving through our galaxy. Our neighboring galaxy Andromeda is on a collision course towards us. This is all due to the gravitational force, in a sense, due to dark matter gluing things together. But then when you take a step back and you look at the universe as a whole, what is happening is everything is expanding. Everything is being pushed further away from everything else. So while dark energy is kind of winning the cosmic battle on large scales, on small scales, dark matter is winning. So gravitational force can pull things together on small scales. This is why our closest neighboring galaxy is crashing into us. But when you take a step back and look at the whole universe, it is expanding. So the question of what would happen if we have another period of inflation now, would it rip things apart? It very much depends on how much the universe grows and how this affects things. Like currently, dark energy is not strong enough to rip apart planets or to rip apart stars or to rip apart black holes. But if the strength of dark energy increases, this is something that we could lead to in the future. So there are several different ways the universe could end. There are many ways the universe could end. But one idea is if dark energy continues behaving the way it is now, at some point, everything is just going to move further and further away from everything else until everything is so far apart that you cannot exchange any energy or any information. This means that you'd look up at the night sky and see complete darkness. There would be nothing clear. There would be no exchange of energy, no exchange of heat. The universe would basically end up as a cold, desolate wasteland where everything is so far away from anything else that nothing can happen. This is what is known as the heat death, the death of heat, the great freeze. Another possible scenario is what is known as the Big Rip. In the Big Rip scenario, dark energy would get slightly stronger in the future, and this would mean that dark energy would be strong enough to actually tear everything apart at the atomic level. So it would start by ripping apart galaxies and then planets and stars, and everything would be ripped apart until even the atoms that make up the basic molecules would also be ripped apart. So the universe would end up as just a scattering of atoms spread out everywhere, not doing anything. This is known as the Big Rip. Fun end of universe scenarios. So going back to the idea of inflation, given that we don't know how inflation would behave, it could do either of these two things. It might be that if we had another period of inflation, it could behave in the same way that dark energy is behaving now, in the sense that it wouldn't rip things apart yet. But if inflation is strong enough again, and assuming it happens everywhere in the universe and so on, it could potentially rip apart not only black holes, but everything. So just using dark energy as a proxy here, we can talk about what inflation might do. But the conditions that were needed to make inflation happen in the early universe, the biggest one was a huge amount of energy. And now that the universe is so big, if inflation were to happen again, it would only be in pockets of the universe and probably not everything, which of course doesn't help you if you're in one of the pockets that is expanding. Okay. Thought from Paul here, black holes evaporate, and as that happens, dark energy and/or a new inflation will grab the emitted particles. Potentially. So there was the question at some point here about what would happen to the information inside a black hole if it's ripped apart, if it evaporates. So the idea of an evaporating black hole is you produce two particles on the event horizon. The universe is constantly producing particle and antiparticle. These annihilate. You produce particles, they immediately annihilate. This is fine. But you kind of borrow energy from the universe to produce a particle and an antiparticle. These annihilate and go back to the universe. But if you if you produce this particle and antiparticle on the event horizon of a black hole, one particle can fall in and one can escape. So then you've you've borrowed energy from the universe to produce these particles. One falls into the black hole. So to pay back the energy that you borrowed from the universe, the black hole loses a bit of mass. This is something that is known as Hawking evaporation. Because this means that the black hole is losing mass, over time, it means that a black hole could lose enough mass that it evaporates. If this happens, what happens to all the information of everything that fell inside the black hole? Is that lost? Does that travel away with the escaping Hawking radiation particles? We have no idea. This is something that is known as the information paradox, because we think that information can never be destroyed in the universe, it can just be transformed. So if it falls into a black hole, what does it become? How do you get this back? Is it lost to us? We do not know. So yeah, we don't know what happens to the information contained in a black hole. Is it all projected onto the surface of the black hole? Really, we have no idea. But that's a very cool question, and one that I personally do not have the answer to. So if black holes evaporate, this kind of causes a new inflation, doesn't seem to be the necessary energy. Like when inflation happened in the very early universe, we're talking about ridiculously high energies. Today, that type of energy is not something that is readily available in the universe in order to trigger another type of inflation. As for dark energy, we don't know what dark energy is. We don't know what dark energy is up to. Okay, there were a lot of black hole related questions there. That was a very long answer. I see another black hole related question here by Breath. I will get to the other one. The lunar landing, the moon landing is a topic I was planning on talking about today at some point. So that is definitely something we're going to get to at some point today in the stream. But while we're on the topic of black holes, let's stay on the topic of black holes. And let me just see if my tea is drinkable by now. Perfect tea. Okay. So, question from Prath here, carrying on with the idea of the supermassive black holes and the stellar mass black holes. On the other side of supermassive black hole, is there a size limit on black hole mass size? Could there practically be a black hole the mass of its entire galaxy that it successfully swallowed? Yes, there could be. So I think the biggest black hole that we have been able to kind of see, or not see directly, but measure, is 72 billion times the mass of the sun. So that is 72 billion suns collapsed into one black hole. That is ridiculously big. That is a huge number. Is there an upper limit to this? Basically, the upper limit comes from, if you believe that supermassive black holes come from stars, then in order for supermassive black holes to form, you have an upper time limit of when they were formed, which is based on when the first stars were formed, which then became the first black holes. Even if you take primordial black holes and say primordial black holes are the origin of the supermassive black holes, you're basically limited by how much that object could grow in the amount of time that we've had. And that is the only limit. There is no other upper limit other than whatever has had time to fall into the black hole, whatever has been close enough to fall into the black hole. So there is no upper limit. You could have black holes ridiculously big, as big as they can swallow. But there is something to remember when talking about black holes. And that we often have the idea that a black hole is like the cosmic plug, like if you're in a bathtub and you pull the plug and everything goes down the drain. And that is true in a sense that black holes are going to gravitationally attract everything around them. But the gravitational force is extremely weak. So the gravitational force decreases with the distance squared. If you get 10 times further away from a black hole, its gravitational pull has decreased by a factor 100. So the further away you are from a black hole, the weaker the gravitational pull is. So while black holes are going to be big gravitational objects that are going to suck things in, if you're far enough away, you're not going to fall into that black hole. There is a supermassive black hole at the center of our galaxy. We are not going to fall into this because we are so far away that, we feel its gravitational presence in the sense that we're part of this big galaxy. But we don't need to worry about being sucked into the supermassive black hole at the center of our galaxy. Right? And the same is true of these 10 million black holes or millions of black holes that we know are out in our galaxy. Are they a danger to us? Probably not, because space is very, 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 very big and very, very, very empty, which means that the chances of a black hole being close enough to affect us are quite small. So the same thing, the point of this tangent here is that if we're talking about a supermassive black hole eating everything up around it, it's not just going to suck up its whole galaxy. It can only really affect the things that are closer to it. Of course, then it might grow and then it can affect more things. But it's not just like, oh, supermassive black hole, everything has fallen into it. There is the fact that we're kind of saved by the fact that gravity is extremely weak. And the further away you are from an object, the less you're going to feel its gravitational presence. So those of you who only just got the notification for YouTube, maybe the notification got lost in a black hole and it was time delayed, and that's why you're just getting it now. Time is relative. So we don't know when you will get your YouTube notifications, but they will come at some point, hopefully while I am still live. Incidentally, I got the YouTube notification half an hour beforehand, so I have a separate YouTube account that is like my personal YouTube account, and obviously my personal YouTube account follows Cup of Cosmology, and I got the YouTube notification half an hour beforehand, as I should have done. So it seems to have been very erratic there. It's also funny because I always get an email like, someone is live on Cup of Cosmology, and I'm like, yes, I hope that someone is me. Otherwise, I have a problem. It's good that I get this email telling me. And I'm like, someone's live on my channel. Oh, yes, it's me. That's who's live on my channel. Okay, a lot of questions. I know I've been jumping through the questions, so I'm just going to scroll back to the beginning, go through all the questions, and see which ones I have and haven't answered. So I know there were a lot of ones at the beginning where we jumped straight into black holes. So let me just go until I get to the one I wanted to answer. Then I'm going to go through and come back to that one. Okay, we did the primordial black holes. That's what started us on the black hole conversation. We talked about eclipses. Okay, then there was a question by James here about I realized your question was not actually about moon landing. I just saw moon landing and jumped on that, but that was not even your question. Okay, so going back to the idea of moons and submoons, we had a question by James about 30 minutes ago by now. Since we are moving back to moon exploration, pin that, I'm going to come back to that. Would satellites or telescopes orbiting the moon give any advantage to our research? Are satellites around the moon even feasible? Yes, they are, and we actually do have satellites orbiting the moon. There is one that is called like the Lunar Reconnaissance Orbiter, which is literally just a satellite we put in orbit around the moon. You very much can put a telescope or satellite in orbit around the moon. As we were saying before, if an object can have submoons, you can also throw a satellite and keep it in orbit there. The Lunar Reconnaissance Orbiter is, as the name implies, studying the moon. It's just doing it from orbit. It's also the one we tend to use when the landers have issues. The one orbiting can be sent to kind of just like look at it, see if you can find it from space, kind of pass information, relay information back and forth. So satellites around the moon are feasible. We have done this. And it's a good way of kind of an in-between step, because especially if you have any landers on the moon, any rovers, these can send information to the satellite, which can then bounce it back to Earth. Because as you might have something, when the moon is behind the Earth with respect to the sun, and there's not much power, there's not much solar energy reaching that, our landers on the moon might not be performing well. So then in order to send their information, they might send it to the satellite that's orbiting the moon, which will then bounce it back to us. So satellites or telescopes around the moon is a very feasible thing, and we have at least one. This is also something we've done with other planets. We sent satellites to orbit other planets to give us information, but we can also send satellites around other moons. There are plans to send ones specifically around moons of Jupiter. The Juno mission is a satellite we sent that did a few loops around Jupiter and then went to do a few loops around its moons and then went back to Jupiter. It's very cool. So yes, satellites around moons are very, very feasible. And I'm sorry that I misread that question, because I could have answered that when we were on the topic of submoons, but that was a good question. And now I've written a note for myself about moon landing, which I am going to talk about at some point. Going through the comments, just making sure that I'm answering them all. The comment from Scotty about recommending stories about different cities in Path of Totality. Yeah. Because this is related to the eclipses, because there are so many cities in the US and North America in general where you will be able to see the eclipse, a lot of cities are putting on events like eclipse watching, and those are very fun things. And if you get the chance to go to an eclipse watching party, you should, because they're very, very entertaining. Okay, going through the comments, I realized I did actually answer quite a few of them. when we were talking about inflation and the expanding universe, there was a question by Paul here. If the universe expands the heat death, which I mentioned before, is this where dark energy keeps expanding, everything gets further and further apart, there's no exchange of energy, no exchange of information, isn't all that information lost? Which would be a violation of information never being lost. Yeah, so it's not that that information is lost, it's just that everything would be so far away from everything else that you cannot exchange this information. So the information is still there, you will just never get to it. You know, information is traveling basically at the speed of light. We talk about the speed of light, but what we actually mean is the speed of information. But if everything is so far away from each other that even traveling at the speed of light, you will never reach each other, then it doesn't matter how much information you have, you're never going to catch up with the expanding universe. If this happens, like, you would look up in the night sky and you would see nothing because everything that could send us light would be so far away. It sends the light, that light would just never reach us. So the information is still there, the information is still traveling in the universe. There's just no receiver. So it's still there, you just can never receive it, which is kind of a very solitary way for the universe to end. But I'm not sure if being ripped apart at the seams is a better end of the universe scenario. There's a comment from James earlier: the enormity of the universe is making me lean towards this being, this in quotation marks, being just a computer program. So the thing I like to ask is, let's just imagine for a minute that everything is a simulation. Okay, we have no way of proving this or disproving this, but let's just say, for the sake of this conversation, that we live in a computer simulation. But this is a computer simulation that is so advanced that we have not been able to see that it's a simulation. You know, we still have some resemblance of, we think, free will. We still have things happening according to laws of physics. We can find some rules of the game. We find some things we don't know. So what changes in our day-to-day life or in our understanding of things if we were in a simulation? Because I think, for me personally, nothing would change. You know, if the universe is a simulation, so what? What does this mean? How does this affect me? It doesn't. You know, if this simulation is so big that, or so incredibly complex, that I still believe that I'm in charge of my own decisions, I still can go about and do whatever I want. Doesn't matter if I'm just like in somebody's Sims games and somewhere. To me personally, it doesn't matter. And I always find that this is a conversation that doesn't really lead anywhere. It's like, what if we're in a simulation? It's like, okay, what if? Where do we go from there? And because it's something we cannot really prove in any way, it's like, okay, maybe the universe is a big simulation, but that's not something that keeps me up at night. There are plenty of physics related things and non-physics related things that do keep me up at night. The possibility of all of this being a matrix, that one does not keep me up at night. Not something that I feel we need to worry about. Comment from Scott: the Kurzgesagt video on black hole stars was pretty good at explaining away the mass gap. There are hundreds of Kurzgesagt. So Kurzgesagt is a YouTube channel that does really cool animations and science outreach. They have a bunch of very cool videos on black holes, and I'm sure at some point they do talk about the mass gap, but it is in general an open question in the field. Okay, I see about 20 minutes ago, I'm catching up with the questions. About 20 minutes ago, still talking about black holes, we had a question from Abyss. Speaking of black holes, were there any black hole merge observed with gravitational wave detectors and radio telescopes? I'm curious if the accretion disk could undergo fusion or emit charged particles along the orthogonal axis. The orthogonal. So that is an interesting question. So when black holes smash together, it's such a violent event that they create ripples in the fabric of space-time. These ripples in the fabric of space-time are what we know as gravitational waves. So gravitational waves are these tiny, tiny, tiny vibrations in space-time. And what happens is when a gravitational wave hits you is it distorts space and time. So first, like if a gravitational wave travels through me, first I get thinner and taller, and then shorter and fatter. But it would not be a noticeable difference. Even if two black holes smash together right next to me, by the time the gravitational wave reaches me, this effect would mean that I would grow by a billionth the width of a human hair. So basically not a noticeable effect. But we have been able to measure these gravitational waves using incredibly precise lasers. I'm not going to go into detail because I did a whole stream about gravitational waves 2 weeks ago. But using incredibly precise lasers, we have been able to measure gravitational waves coming from black holes smashing together. Now, there are several different types of gravitational waves we have been able to measure. One is from black holes smashing together. And another very interesting one is when neutron stars smash together. The reason neutron stars are interesting when they smash together, especially, is because they produce both the gravitational waves, but they also produce what is known as the electromagnetic counterpart. So in the electromagnetic counterpart, what we mean is the neutron stars smash together and they emit both gravitational waves and electromagnetic radiation. In this case, when the first time this happened in 2017, we were able to track this across the whole electromagnetic spectrum. So it started with the gamma ray burst, which arrived at exactly the same time as the gravitational waves. And then you got the whole thing, it shifted into all of the gravitational wave spectrum. You got to see it in infrared, you got to see it in visible, you got to see it in microwave. We also got to see it in radio. Now, as for the question here of could you get a radio wave counterpart of two black holes smashing together? I'm not sure. In principle, I would say no, because black holes do not usually have this electromagnetic counterpart. But I guess the direction you were heading with this question is black holes can have magnetic fields associated to them. When these magnetic fields crash together, they could actually produce superluminal, like not superluminal, sorry, really fast, like highly heated electromagnetic radiation, which we could then hope to see. I'm not actually sure. I've not heard, this is not ringing any bells like something I've heard about, but it is a very cool question. So I'm going to look into that. That's a very cool question, Abyss. So thank you for that. So if the accretion disks, of course, the accretion disks around the black holes is a whole other thing. Okay, let's rethink this. So the accretion disk, I'm actually going to use my trusted plushie here. If I have a black hole, this is my black hole. Let's ignore the fact that it's white on the other side. We have a black hole. It's going to have this disk around it. This is the accretion disk. This is matter falling into the black hole. Now, usually these big accretion disks become a thing when we're talking about supermassive black holes smashing together. Now, normal black holes, stellar mass black holes, don't have much of an accretion disk that would be noticeable when smashing together. So the question that I just answered was about normal black holes smashing together. We're not likely to get any electromagnetic counterparts. However, if you have two supermassive black holes smashing together, then you might have the accretion disks doing funky things, which could produce the electromagnetic counterpart. We have not yet been able to directly confirm supermassive black holes smashing together. This is something that we are hoping to measure in the future. For an example, with the LISA experiment, the Laser Interferometer Space Antenna, which is a gravitational wave detector we are sending to space in 10 years, and that I'm working on. Very cool. And that one will be looking for gravitational waves coming from supermassive black holes. And if this is close enough and kind of loud enough, there is a chance that we could find the electromagnetic counterpart of these. So yes, I answered your question. I read half of your question and answered it for stellar mass black holes. But if we think about accretion disks, then we go into supermassive black holes, and then you could have an electromagnetic counterpart. Okay. There's one more coda question. Sorry, not coda. There's one more black hole question. I just read two comments together. One more black hole question. And then I'm gonna change gears and talk about the moon landing, because someone told me in advance they were going to ask. They're not here, but I'm going to answer it anyway. Okay, so one more black hole question. Are all event horizons perfectly spherical? Event horizon around a black hole, for anyone who isn't familiar with the term, is this point of no return. I was glad to went to 1.25 to catch up. Talking fast reminded me of Periscope days. Yeah, I used to, people tell me I still talk fast, but I used to talk a lot quicker. This is the slow version of me. But yes, if you want to get a reminder of how my early streams were when I was still not really fluent, not really good at communicating, in my personal opinion, my streams have improved a lot since then. But the earlier days, I was trying to get as many words out as possible. So if you want to recreate the early Periscope days, yeah, that experience, just watch me on like 1.5 speed and you'll recreate it quite nicely. Okay, so the event horizon, for anyone who isn't familiar with the term, is the region around a black hole that is kind of the point of no return. Once you hit the event horizon, you would need to travel faster than light in a vacuum in order to escape. So the event horizon is kind of the point of no return. Imagine this is the event horizon. Before you reach the event horizon, you can still turn away. It would require a lot of energy, but you can still escape. Once you hit the event horizon, you're kind of inside the black hole. There is no turning back. You can no longer escape. Now, if we consider a black hole as being like a star that's collapsed, it's probably going to be a sphere. The event horizon is probably going to be a sphere, but it doesn't have to be. You can have things, for an example, if you have two black holes smashing together, you can actually end up with an event horizon that is a donut. a torus with the black holes kind of like here, and then the donut going around them. Donut like this, imagine you're looking at it from above, one black hole here, one black hole here. These are kind of smashed together. This is how the event horizon ends up. So event horizons do not necessarily need to be spherical. A lot of things in the universe are spherical because it's just energetically more efficient to create circles than literally anything else. But you can have event horizons that are not actually spherical. However, they're not as easy to realize. So usually we think of event horizons as being a sphere around the black hole. Abyss saying you missed the RWTH scopes. Honestly, me too. So during my PhD, I set up a second live stream once a week with people in my office, and it was really fun. And then you had the Cup of Cosmology streams on Sundays, and the RWTH ones, like my university in Aachen on Wednesdays. It was so much fun. But once I left Aachen, those things disappeared. They did not keep it going after I left. And it's a shame because it was really fun. And I feel like I have not got enough people to do it at my current place. Like people join these streams occasionally, but not enough to do it continuously. And honestly, managing 2 of these live streams a week during my PhD was a huge amount of effort, and it was exhausting. And I'm very, very happy to do Cup of Cosmology. I don't think I have energy or time to set up a second live stream and manage it and find the guests and the topics every week. It was a lot more work than I think people realize. I'm glad I did it, but I'm not going back to that. Okay, so another topic I wanted to touch upon briefly today is moon landings. And the reason I want to talk about this is because a couple of days ago, there was the first ever commercial, like private company landed on the moon. So this is both very cool and something very worth paying attention to. So going to the moon is expensive. Sending things to space is expensive. It requires a lot of money. At some point, NASA realized that it's just a huge amount of money to build the rockets, to send them to space, to do the payload, to do everything, to get things to the moon is a lot of money. And it's something that, when NASA is doing it, this is funded by taxpayers' money. So of course, it's worthwhile and it's worth doing. But at some point, it is a lot of money. So a couple of years ago, NASA opened a call for private companies to kind of being involved in this. And the idea is that these private companies build the rocket, arrange the launch, and get the stuff to the moon. And then NASA pays to put its science missions on these rockets. So rather than building a whole new moon lander, NASA and paying for the launch and everything, NASA pays to put its stuff on someone else's rocket. Now, the idea behind this was to create, a new space race among companies competing against each other to be the first companies to go to the moon. And then NASA would kind of piggyback on this to take its own scientific missions to the moon. It is a very nice idea. There have been a couple of companies that have got involved in this and companies that have kind of signed up to send these rockets to the moon. But this comes with good and bad things. So this year, we've already had 2 attempts by private companies of sending stuff to the moon. The first one was a couple of weeks ago, and it was not successful. The satellite, or the thing they were planning on landing on the moon, had an issue during takeoff, during launch, and they realized that they managed to get it into like low Earth orbit or into orbit, but they realized that it was not going to make it to the moon. So they did the next best thing and they brought it down and kind of burnt it up in the atmosphere. It was kind of the safest way of bringing it back down. Then this week, a few days ago, there was this lander that actually made it to the moon. Why wasn't the launch of this lander in the news? I'm honestly not sure, because it was in my news. Like, I saw it. There's some web pages you can follow, like Spaceflight Now, which will give you every possible rocket launch you could think of. And I saw this one in my usual news as well, but it wasn't as hyped as, for example, SpaceX, because SpaceX is very, very, very good at PR. So they hype up their launches a lot. This one wasn't as overhyped as some of those, but like I was definitely aware of when the launch happened. So it was in some news things, but it was not as widely hyped because there wasn't as much PR around it. So this is a private company. I cannot think of the name. Mission Inventive, something like super dramatic, Machines Inventive, something like that. They almost completely successfully landed on the moon 2 days ago. Their orbiter, or not their orbiter, sorry, their vehicle tipped over. So it landed on the moon and then fell over. They're not completely sure why, but it's on its side. This means that it's not getting as much light as it should, but the positive thing is that all of the science experiments are on the side facing up, and on the side facing the bottom, there's none of these science experiments. So they think they will still be able to carry out the science with this mission. Okay, so is this a good thing? This is a big question, right? I know nobody asked, but I'm asking myself, is this a good thing? On the one hand, it is getting us back to the moon. Applied ideal mechanics? No, it's something like MI. It starts with the first one is like machine, second one is something like inventive. It's something like that. But on the one hand, this is very much creating interest in people going back to the moon. It is making it easier for NASA to get scientific experiments on the moon. If there's private companies doing this and NASA can piggyback on it, NASA can basically get more stuff to the moon without needing to worry about launching it there. So on that side, it is good. And it has created this competition of companies competing to be the first ones to do this. Intuitive machines, thank you. Yes, intuitive machines. That's what I had in my mind. I am not MI. Yes, I was like missions, machine, impossible, something like that. Intuitive machines, that sounds exactly right. Okay, so of course it has created this push and companies are competing. But at the end of the day, companies are always going to focus on profit. They are not doing it for the scientific endeavor of being involved in the space missions. They are doing it for profit. It is a business. Which means at the end of the day, the decisions made are always going to be economical decisions. What makes the most sense for the business? If at some point it makes more sense for the business to cut off its ties with NASA and carry on doing the privatization part, they will do that. As someone who, as you all know, I am very much not a fan of capitalism. And this idea of giving private companies all of the power to decide what happens on the moon is something that I am personally rather skeptical of. Then there's the other big thing that we need to consider, that currently we don't have regulations on the moon because the moon doesn't belong to one country who can regulate it. The moon doesn't belong to one state that can impose its own laws there. Which also means there's not a lot of market regulation, for an example. There is not much going on in terms of the rules of how people should behave or act on the moon. So now we have a situation where we have companies which are going to operate for profit and a moon where there is not much legislation. This could be very good for a lot of things, but it could also backfire. And the clearest example of this, in my mind, was already seen in the first mission that failed a few weeks ago. Because that was a private company, apart from some science missions, they're also going to sell off space on their mission to do other things, right? Because if they're sending it up to the moon, they're going to want people to pay to send it to the moon. So this one, a couple of weeks ago, a couple of very wealthy families had paid to have remains of their relatives on board this lander that was going to land on the moon. And the idea was kind of to scatter the ashes on the moon. Is this ethical? Does the moon belong to someone? Is it public property? Is it, is it reasonable to bring human remains to the moon? Especially considering that for a lot of indigenous people, the moon is sacred. The moon is not a place where you should bury a body or, scatter ashes. So this was a whole ethical conundrum where a lot of people asked, like, please don't send these ashes to the moon until we have regulations with this. However, this private company went ahead with it. Then, of course, they did not succeed, and their mission, their spacecraft, burnt up in orbit, with the ashes also burning up in orbit. I'm not sure if that's what the deceased would have wanted, but also, So that is just like one example. But what if the moon becomes like a real estate game? What if someone goes to the moon and thinks, while I'm here, why don't I just plant a big billboard advertising my company? I paid to get us to the moon. Am I allowed to advertise on the moon? Well, currently there are no regulations against it. And then what if we find minerals on the moon or products on the moon that are very useful? Who has a right to them? Who has a right to go mine these? Does anyone? Should we do this? I think these are all ethical questions. I don't have the answer to all of these. But these are ethical questions that we should be asking. And the time to ask them is now, not 10 years down the line when we've sent 20 different companies to the moon and each has done its own thing. At the end of the day, once we privatize this, it becomes a for-profit business. So I have very mixed feelings on this. On the one hand, it is good that we now have multiple ways to send scientific missions to the moon. It's something where we really can bridge the gap between private companies and state-funded things like NASA. But are we doing this in an ethical way? Are we aware of the consequences of our actions? Are we ready for the moon to become the next big advertising spot for private companies? Are we prepared for the moon to be exploited by whoever gets there first, by whoever has the most money to send a mission to the moon? There's an example that Ben is mentioning here of H3, helium-3. Helium-3 is something that we're pretty sure there is someone on the moon, and it's something that can be used in building processors and computing down here. This is like an untapped resource. Whoever gets there first gets first rights. Is that the way we should be doing this? So I think I'm all for space innovation, but I'm very reluctant of turning the moon into the next commercial enterprise. And I think this is something that we've also seen in terms of not just the moon, but space exploration in general. SpaceX is the clearest example here. Musk wants to build a colony on Mars, and it's going to happen whether regulations get in the way or not. Is this the right way of doing things? And I feel like these are questions that we should be having before we allow these companies to privatize the moon, to privatize spaceflight. So I see Abyssia saying that this sets a dangerous precedent. Commercialized space exploration can always go wrong. Yes, it might not. It might not go wrong. It might be a good thing. It might bring about another scientific revolution in terms of space flights. But also, at the end of the day, these are companies that are going to prioritize their profits. And whatever else we say about it, they are going to prioritize their profits. And if it's more profitable at some point to ditch the science and focus purely on let's build a Starbucks on the moon, who's going to stop them? Currently, we literally cannot stop them. So this is something that I think we really need to discuss. Comment from David Howden here. I doubt you'll have regulations on the moon unless we get a world government or one dominant national superpower that can enforce its will on the rest. This is the other thing, right? Like, who would you want to set these regulations? Do you want the US to regulate the moon? Personally, hell no. Who do you want to regulate the moon? Who should be in charge of this? This is also a question that I'm not saying this is easy. I'm not saying there's a clear solution or a clear step forward. But it's something that I think is a vital part of this conversation. And it's something like that I think we really should be talking about while this is happening. So the reason I wanted to talk about this, someone sent me a message saying, I'm going to ask you about your opinions on the moon landing, about this privatization. So I was thinking earlier, like, what are my opinions on this? What are my thoughts on this? And I love the idea that there are more science missions going to the moon. What if at some point there's a science mission there and they realize there's also a pocket of helium-3 there? What is priority, the science mission or drilling to get the resource? Well, the company is going to prioritize whatever brings it the most profits because that's how businesses work. Is that the way we should be doing space exploration? That is a big question. So yeah, I very much do not have the answer. I'm not confident that various government uses of space will always be ethical either. No, this is the thing. If you think back about space exploration, when during the space race, when we were racing to be the first to get to the moon, was it ethical that animals were sent to space? Let's test it on an animal before we tested on a human. Was that ethical? In hindsight, probably not. 100 years from now, what are people going to say that we're doing that is very unethical? We will always be judged by the standards of the future, and that is a good thing. Future moves forward, progress moves forward, and we will always be judged by the standards of tomorrow, and this is okay. But yeah, so I think space exploration in itself has issues. Commercializing space exploration brings a whole other bunch of issues. So while it's exciting, and it's slightly sad and also slightly funny that the lander is on its side, it kind of fell over. It's kind of very comical, but apparently it fell over in a way that the top is resting on a block, so it's like perfectly horizontal. It's not even slanted down. It's like, I'm going to sleep here. It's very comical. But yeah, I think there's a lot of important questions we should ask ourselves, and I think the time to ask these questions is now, not 10 years down the line and we're like, oh, whoops, we should have regulated this before letting private companies have access to the moon. So yeah, that is a long answer, 15-minute thing there. That is basically me ranting about the privatization of the moon. But I think people could have seen that coming because, of course, that's how I'm going to answer the question. It is consistent with how I've always answered these questions. But please do let me know your own opinions. Of course, this is something that it's important to discuss and it's important to have these conversations. If you disagree with what I'm saying, please do let me know. I see a bunch of people kind of agreeing with what I'm saying or the general sentiment. If you have a reason why you think the commercialization is the way to go, just let me know. Let me know what you think. Let me know your thoughts. I always do read the comments. I know some of you then come in and watch the replay and leave comments. I do actually read them. Sometimes YouTube doesn't notify me and I go back and read the comments. So feel free to, let me know your own thoughts. Get in touch if you have a different opinion, if you share my opinion, whatever. I think this is something that is a very interesting conversation to be had. And it's something that I'm always happy to discuss. So if people have different opinions, please do let me know. Okay, we have gone over the 1 hour mark today because I spent about 45 minutes talking about black holes, which is a very fun topic. And then 15 minutes talking about the moon landing or the privatization or commercialization of these things. A few bit of stuff thrown in and we're at the 1 hour mark. And something that I cannot let this stream end without doing. We are 1 hour, 6 minutes into the stream and I still have not flashed the best image in the universe. The snapshot of the baby universe. If anybody thought I was going to let the stream end without flashing the cosmic microwave background radiation, rest assured, there is always going to be at least one appearance per stream of this image. But I'm not going to go into it today. If you don't know what that image is and why it's important, tune in next week and I can tell you about it next week. Not going to do it now because else we'll be here another half an hour. But if you don't know what that amazing pretty image is and you do want to know what that amazing pretty image is, ask me next week. We can do a whole stream about that if people want to. Okay, this has been super, super fun. I loved all of the black hole questions. I like that we had so many related questions today. These streams are always, let's see where we go. And sometimes I talk about 20 different topics and sometimes it's like 2 or 3 topics. And then it's also fun because then I go back and I edit the video descriptions. You'll see there's just like generic questions here, like what is dark matter? And then I always go back and edit it. And of course I'll edit it to what are black holes? How do we study them? So it's very cool that we all stay kind of on black holes today. There's a lot of stuff to talk about with black holes. You are beginning to doubt if this is Cup of Cosmology. I mean, the cosmic microwave background is in the Cup of Cosmology logo, so you do always get it at the start of every stream. But yes, it does have to appear. To everybody watching, as Paul is just saying here, if you haven't done so yet, please do like the video, leave a comment, subscribe, all of the usual YouTube things. It really, really, really does help. If you're watching on Twitch, you can also press lots of buttons on Twitch, make stuff happen. I do see Twitch comments as well. So please do press all the buttons, make stuff happen. I really do appreciate it. As always, if you want to request a topic, you can go to cupofcosmology.com. There's a section where you can request a topic. In exchange, I ask that you do a donation to one of the organizations that I care about, and then you can request a topic. And I'm always open for topics. If you have a guest who you think should be on my stream, let me know. We can always arrange that as well. Okay, this has been great fun. Thank you everyone for tuning in. Really, I really love these science chats that we have every weekend. I really do appreciate that you all still tune in. So thank you everybody for tuning in. Cup of Cosmology should be online next Sunday, same time as today. That is 8 p.m. in Finland, 7 p.m. in the rest of Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out the timing of the next stream in your own time zone. But unless something unexpected happens, you can expect me here next Sunday, same time as always. I hope to see you all again next Sunday, same time as today. And I hope in the meantime, you'll stay safe and take care of each other.